All right. So if we look at example 3.4.2 here, we're looking at this method and its selectivity coefficient. So to determine how selective it is toward its analyte, which is codeine. And we have an interferent, something that gets in the way, which is 6-methoxycodeine. Okay? And we're also privileged to have some signal information. We're told that the codeine, example of codeine, at concentration of X, it doesn't tell us what concentration, gives a signal of 40. And at the same concentration, the 6-methoxycodeine gives a signal of 6. And we want to determine what the selectivity coefficient is for this information, for this assay, for this method, based on this information. Okay, so the selectivity coefficient is pretty straightforward to think about. Some things that we should hopefully already have in mind that are the signal from the sample is equal to the concentration of our analyte times the proportionality constant of the analyte plus the concentration of the interferer times the proportionality constant of the interferer. Okay? So, our proportionality constant, or our selectivity constant, the selectivity constant, the big K here, which is symboled KAI, is equal to the proportionality constant for the inhibitor over the proportionality constant for the analyte. Okay? And this ratio tells us how good selectivity this our given method is for our analyte. Well, we can also say that for situations where, like the one provided, where the two concentrations of the analyte and the interferer are the same, that's what we're told here, right? That equimolar solutions of codeine and the interferent are the same here, then we can also see that under those conditions, Ki times the concentration over Ka times the concentration of the analyte, this is the concentration of the interferent, right? That also equals this. Okay? And we know that for our sample here, we have some data, right? We know that the S for the analyte, concentration of the analyte times the constant for the analyte, this equals what?
Is that the 40?
That's right, because the 40 is the signal given for our given concentration of our analyte. And then we also should know that Ki is equal to what?
That's the signal for the interferent.
That's right, the signal for the interferent. And what value is that?
Is that 6?
That's right, 6. So, together, right, what is this going to equal to here?
That's 46.
That's right, 46, because this is the signal for our analyte, this is the signal for the interferent, and the signal of the sample is the combination of these, right?
Okay, yeah.
Okay, good. So, let's give ourselves a little extra space there. Well, what we can see is, essentially, for this, KICI, which equals 6, and this, KACA, equals 40. Now, this is not true only if what?
What do you mean?
Well, the selectivity coefficient does not equal this statement unless the CI here and the CA are the same concentration.
Oh, okay, yeah.
So it's only good for our specific scenario. But because we have this scenario, we can utilize that information, and we can see that the KCI, the KICI, this one up here, is equal to 6. And that the KCAKA same thing here, equal to 40. And so we can get our selectivity coefficient just simply by that, which I think is 0.015. Is that right? Okay, good. Now, for part B here, they want to know what concentration of coating with an accuracy of 0.5%, what is the maximum relative concentration of the interferent that we can have? Okay. Now, they walk us through the rearrangement of our initial equation, two of our initial equations, to make them fit together, and they say here that this value here needs to be less than the 0.5 times that value. And that's true, but I don't feel like that's very intuitive. So I want to walk us through it a little bit of a different way here, okay? So let's look at what we do know. We know that the signal of the interferent at the concentration of the interferent was, as provided initially, was 6, right? And this is at the proportionality constant, or with the proportionality constant for that interferent. Well, we know that the signal for our analyte, the concentration of the analyte, which is the same as that concentration there, the proportionality constant for that concentration. Do you remember what this one was?
That was 40, right?
Yeah, that's 40. So let me bring up the problem here to make sure that we can see what's going on here. This was the information that was provided to us, right? 40 and 6, right? Okay, very good. Now, we've decided that we only want a signal contribution from the interferent of 0.5%. 0.5%. Now, what's 0.5% of 40?
Is that 0.2?
That's right, it's 0.2. Okay, so what I want, or what the allowable, the acceptable signal from the, we're going to call this the signal acceptable from the interferent, is not 6, but 0.2. And that is going to occur, this Ki is the same, it's going to occur when this is at an acceptable concentration. And that's what we're trying to figure out. What is the acceptable concentration? Okay. Well, I can take these two equations here and see that essentially I have two equations with one unknown, or sorry, two unknowns, the Ki here and the Ci and the CIACT, the acceptable concentration of the inhibitor, and I can combine them together in a ratio basically. So if I say that 0.2 over 6, let's take this one here, equals to this acceptable times the Ki over CIKI, and this is the Ci at whatever concentration. They didn't tell us what that concentration is, Ki. The Ki's cancel out, and I'm left with this ratio equaling the Ci acceptable over Ci. Now, we still don't know what that was, but we do know something about that. We do know that it was equal to the Ci was equal to, in this case here, the Ci was equal to the concentration of the analyte. Do you remember that?
Oh, because it says equimolar solutions?
That's right. They have the same concentration, right? So this Ci, that concentration, is also the concentration of the analyte. So that's good there. It shows us the ratio of our acceptable interferent to the ratio of the analyte. Okay? So 0.2 divided by 6 there, 0.033. That's our ratio times 100, 3.3%. So of whatever concentration of analyte you have, you can only have 3.3% of it as this interferent. Okay, so that's a little more intuitive to me. We can see that this ratio here can be found by combining these statements. Again, this one was given to us, this one was given to us, and this is what we said we wanted to have, so we had to identify what that concentration was. Okay, very good. Now, here's another example, 3.42. Mercury is also an interferent in the fluorescence method, in a fluorescence method for the silver ion. The selectivity coefficient is provided for us, -1 times 10 to the minus 3. And now the fact that it's a negative value, what do you think that means?
Negative value. Well, does that mean it suppresses the signal?
That's right. That's right. So if you have the silver ion in solution, you'll get a signal X. If you put mercury in there with the silver ion, the solutions or the signal will be lower, right? Because it's going to be suppressed. All right. So that's good. What is the significance of the selectivity coefficient negative sign? We just talked about that. So suppose we want to plan to use this method to analyze solutions of silver, no smaller than 0.1 nanomolar. What's the maximum concentration of Hg plus 2 ion you can tolerate if your percentage relative error must be less than 1%? Okay, less than 1%. Well, you can look at the answer there afterwards and try to follow what they ask you to do, but I feel like that they kind of just tell you the equation and ask you to trust it. I don't feel like it's very intuitive. So I'm going to, we're going to talk our way through this one as well with our standard group of equations that we already kind of have, that we're already familiar with. Okay? The KAI here, which is the KAGHG, right? Which is our selectivity coefficient. It equals -1 times 10 to the minus 3. Right?
Yeah.
And in terms of activity, in terms of proportionality constants, what is KAI equal to?
It equals KI, little ki,
Very good.
over Ka.
Very good. The proportionality constant for the interferent divided by the proportionality constant for the analyte. All right. Excellent. Now, if I add in this information, Ci and Ca, will that still be equal to KAI?
No, because those are different you don't know what their concentrations are.
All right, but what if I assumed that their concentrations were the same value, right? Then they would just cancel out, right?
Oh, okay, yeah, I guess so.
So if we assume that these two concentrations were the same, then we could leave those there for now, right?
Yeah.
And then I could solve this, rearrange this equation to have it be equal just to the Ki-Ci. So if I have, I'm going to rewrite it Ci-Ki. If I have this, and now I set it equal to, it's going to be the -1 times 10 to the minus 3 times the Ca-Ka. All right? You see what I did there? I just said, this is equal to -1 times 10 to the minus 3, but I solved for the Ki-Ci.
Okay, but why did you want to do that?
Well, because we're again being asked, what is the concentration of the analyte, the concentration of the interferent, the maximum concentration of the interferent that we can have under these conditions. And so if we have the Ci in our equation here, if we solve for Ci and then relate that to our other standard equation that we have here, the S for the sample, right? The signal for the sample. What is the signal for the sample equal?
The sample signal is from the the concentration of the analyte times the proportionality constant for the analyte, and plus that to CI/KI.
Very good. And CI/KI is, again, the concentration of the interferent times the proportionality constant for the interferent. Okay? So, S sample there. Let's say that for some sample, we got 100% signal for CA/KA from our concentration of analyte. And what kind of signal are we allowing or expecting for our interferent?
The interferent, what kind of interference can it do?
Yeah. Do we know how much we are going to allow the interferent to interfere?
Well, the error must be less than 1%.
Very good. So 1%. So if I'm going to change this by 1%, how is it going to change?
1% of 100 is 1.
That's right. So it's going to go down to 99. So CA/KA with the CI/KI, which is just this up here, that we're going to allow to be 99, right? We're only going to allow 1% change. And that's what our shift in 1% there is. Now, what about, so what does that tell us that CI/KI equals to? Now, this is not just this CI here. I don't want to confuse us into thinking that this interferent concentration is the same as this interferent concentration. This is the interferent concentration where you have the concentration the same as the analyte. This interferent concentration is what we will call the acceptable interferent concentration. So at the acceptable interferent concentration, what kind of signal are we going to get?
Well, let's see. I don't know. How can you tell?
Well, see, the sum of these two, this one and this one, equals 99, whereas this one all by itself is 100. So what does that one have to be?
Oh, -1?
Very good. -1. So what we have here now is two equations that both contain different concentrations of this CI, but we can use them as a ratio to identify the relative relationship between the acceptable, and because this CI equals the analyte, whoops, down here, right? In this case, the CI equals the analyte. We're going to get a relationship between the acceptable to the analyte. Okay, so I'm going to copy this down here and say that CI acceptable times KI, which equals -1, over CI KI here, but where this CI actually is CA, right? Why is it CA?
Well, on the left there, this equation here, yeah, you said that that was only true if those were the same concentration.
That's right. So I can take this CA here and multiply by the KI there and say that this value here equals the rest of that information. Okay, so I got this is the information on the bottom, -1 times 10 to the -3 CA KA, and that's all under this value here, which is -1. All right, and now the concentration of, also these KIs cancel out over here, so we're solving for our ratio, our acceptable ratio here, and this CA/KA here is going to be this 100, right? It's going to be the concentration that, or the signal, sorry, that we would expect from this concentration over here. So -1 times -1 times 10 to the -3 times 100. Okay, very good. So if I solve for this, that equals 10. So the ratio of the concentration of the interferent to the concentration of the analyte for a sample is going to be 10 times the concentration that you're measuring. So in this case, we're measuring 1 nanomolar. So that means that our acceptable value here, acceptable concentration, is 1 times 10 to the minus 8. 1 times 10 to the minus 8. Or 10 nanomolar. Okay, very good. A lot of calculations there, but hopefully you have time to learn how to do those, and we'll have just a couple problems. We're not going to spend a lot of time there, but it's important to know where to go to answer those types of questions. Again, not necessarily as much for this class. We'll do a little bit, but moving forward in your careers. All right. Let's have a conversation about the relationship, or the terms robustness and ruggedness. A method is considered to be robust if a wide variety of sample matrices. Now, we haven't talked about the matrix much, or the matrices. The matrix is everything that's in your sample that you're measuring that's not the analyte. So there's always something in the matrix, even if you say it's just water, right? There's always something in the matrix, and it can influence the reaction. If a chemical reaction is, if a method is robust, then that means that it will not be bothered by different things that are in the matrix, different interferences. Okay. If a method is considered rugged, this is referring to the ability to handle slight changes in reaction conditions, not in concentrations of interference necessarily, but changes in temperature, changes in pH maybe, changes in reaction time. If it's rugged, then these changes aren't going to affect the results. Scale of operation. This section here I don't want you to spend too much time on, but essentially they provide a chart for us to look and recognize the relationship between the massive sample that you have and the concentration of the analyte in that sample. And as the concentration of the analyte in the sample goes down, then the massive sample here goes up, right? So here's 1 times 10 to the minus 1, minus 2, minus 3, minus 4, right? So it's getting smaller. The sample mass is getting smaller as I move to the right. And there's some fairly interesting stuff here, but nothing that we're going to be tested on, so let's not spend too much time there. Now, we've talked about this already, but there are many parameters. Time, cost, equipment, which is wrapped up into time. Right? All of these factors kind of, at some point, will play maybe even a more important role than accuracy, depending on what you need to get done. We would expect the most important parameter to be accuracy, but turnover time could be more important. Our current system of trying to assess the importance or the impact of the coronavirus is showing that time is so important to us for certain questions. Does this person have the coronavirus? Does this person have antibodies for the coronavirus? Does this person have symptoms, right? Because of all of these different parameters, these different, the importance of knowing these things quickly, we're also getting a fair amount of incorrect measurements, right? But the information as a whole to the scientists at this time is more important than the accuracy. And so they're pressing forward. And that's even the case with the vaccine, right? That's not to say that the risk is great. It's just to say that sometimes the cost associated with making the method quick overpowers the cost associated with having the correct answer or the at most accurate answer. All right, and again, this is all kind of basically what we've been talking about. The final choice can be kind of convoluted. It's not always cut and dry. there are a lot of parameters associated with the method that you decide to use. So, how about the procedure? How are we going to develop our procedure? We need to somehow compensate for any sort of interferences, right? If we could. The signal, the total signal that a sample gives, is the signal from our, we'll always focus on the concentration one. Notice that they give two equations here. One is for moles of material and one's concentration. We'll just talk about the concentration perspective for now, right? But recognize that there's always two equations whenever concentration is considered the number of moles. This, again, being a total analysis and this being an instrumental analysis. So the total signal is related to the signal from the analyte plus the signal from the matrix, we say, or the signal from the reagent, the solvent, right? And there's going to be some signal. It's not always a lot, and it might be negative sometimes, but we do have to take that into account. Okay. Now, to determine, therefore, to get the signal from our sample, from our analyte, we have to subtract the signal from our matrix or our reagent from the signal total. All right, and that signal there, or sorry, this signal reagent component is called a blank, a method blank, right? Where we run the sample. So, for example, it says here, a procedure in which we dissolve 0.1 gram sample in a portion of the solvent and add the different reagents and dilute, do all the different steps. That would be an example of a sample. But a blank would be an example of doing the exact same dilutions, everything exactly the same way, but we don't include our sample. We don't include our sample. Now, if the sample volume is critical, if it contributes to diluting the rest of the reagent down, then sometimes you'll want to make sure you add something that would perform the equivalent dilution, the equivalent change in volume, all right? Some inert compound, and it's usually just the solvent of whatever it is that you're using in an experimental method, right? So it doesn't necessarily mean that the blank is a perfect compensator for an interferent, but it can contribute to general low contributing interference, right? All right. So we also always need to have a calibration, some sort of way of identifying signal and relating it to the concentration of the analyte. And generally this is done by a calibration curve, also known as a standard curve. We call it a standard curve because all of these were concentrations of our analytes that we made. So we know the concentrations of those analytes, and they were the standards that we created. We ran them in the method, and then we see a linear relationship. Now this relationship here is a good sign, right? Because it shows you that the response is related to the amount of material. If you ran this method for some unknown concentration and got a given response, you could use the equation of the line, y equals mx plus b, to identify what the concentration of the analyte was. Okay. Sampling. Sampling becomes very important. There's proper strategies. You can't be biased or non-representative. For example, if you take a little bit of water from a lake, but you take it in a place where it's by the shore or it's by the source of the pollution, right? That won't give you a good representation of your sample. Validation. You need to validate your process, and essentially what that is to validate your process is to get standards, other standards that you know. And again, a standard curve is a good way to show that you've validated your system. Now, if your method, now if your sample has a different matrix in it, then that's a problem, right? And that's why it's always nice to create the standards in the same matrix as the sample. And we'll talk more about that later. Okay. Very good. So one last little conversation about protocols. Agencies, federal labs, state labs, they'll often provide protocols or have designated protocols which contain quality assurance and quality control. And the goal is to ensure that the lab work is accurate and precise. And you'll often have the instructions that will allow you to work through and make sure that your resulting values are within a threshold, which is usually about 10% of the expected concentration. So a given standard is also provided or expected to be used. All right, and after your successful analysis, then that's when you can show the concentration of a given unknown and use it to either submit it to a lab or to convince others of the accuracy of your method or the actual concentration in a sample. Okay, very good. Chapter 3.
Thank you.